Okay, good morning, students. So, this is the 12th session. Okay, and today I'm going to talk about the all important modulation theorem. Okay, so there was no noise, right? So, the whole of communication would have been encompassed in this theorem and the two important properties of impulse functions. Okay, so first things first. So the first important property of an impulse function, okay, so is the shifting property. Okay, so the shifting property tells you that if I have a signal x of t, okay, and I convolve it with an impulse that's somewhere else, not at the origin, okay, so the origin of the signal x of t gets shifted to the point tau. Okay, so for example, if my x of t was this, okay, so this is minus t1 0 to some t2, okay, and how does delta t minus tau look like? So delta t minus tau is an impulse, okay, which exists when the term inside the bracket is 0, that is at t equal to tau. Okay, so the strength of the impulse is 1, so this is the impulse. Okay, now the result of this convolution is nothing but this. So I have the time axis, so whatever is at 0 will now get shifted to the time tau. Okay, so I have x of t minus tau, so if you plot it, you will get the same shape. Okay, so this is my time axis, so here was my origin. Okay, so whatever was at 0 here will now get shifted to t equal to tau. Okay, so this point here will be tau minus t1 and this point here will be tau plus t2. Okay, so it doesn't matter what the argument here is, so it always holds. Okay, so you can call tau, eta, whatever it is, right? So the property is this, so if you convolve, so the waveform gets shifted. Okay, so this is called as the shifting property of an impulse function. Okay, so we have impulse function in the frequency domain as well. So if I have some spectrum, okay, and I convolve it with, okay, so I'll get, okay, so the same thing happens, right? So instead of this being x of t, now if this was x of j omega, so there will be two parts. So as we have seen in the previous example, x of j omega is in general a complex number, right? So it has a magnitude as well as a phase, so I'm assuming it's real. Okay, so suppose these 2 points were, this was omega 1, this was 0, and this was some omega 2, right? And this was omega axis and this was omega naught. Okay, so what would have happened is this would have been omega minus omega 1, so this point would be omega naught and this point would be omega naught plus omega 2, and the axis in all the cases would be omegas. Okay, so what I'm trying to tell you is that, so it doesn't matter what the argument is. Okay, so if it's a function of time, whether it's a function of frequency or whatever the variable is, right? It can be a function of, say, the distance. Okay, so your x-axis, y-axis, whatever, when you convolve it with an impulse function, so the whatever the function you are convolving will get, the origin gets shifted, okay, by the appropriate amount, okay. So in this example, so when I convolve the time domain functions, okay, so what happened was the origin got shifted by the amount t naught, okay. So the frequency here is getting shifted by omega naught, okay, fine. So this is the shifting property, right? And next, as we have seen, the periodic signals are represented as in terms of Fourier series, okay. So where AKs were called as the spectrums, or they were called as the line spectrum, okay, because you had lines at different discrete intervals, okay, at k equal to the integer values going from minus infinity to plus infinity. Now, so to bring all under one umbrella, right, so what I'm going to do is I'm going to define a Fourier transform for a signal, an complex exponential signal, okay. Now, so if x of t is equal to 1 for all t, okay, so if you plot this signal, you'll get a DC waveform, okay, like this. So it extends from minus infinity to plus infinity. So x of j omega is, for this, the Fourier transform is delta omega, okay, right. So you have an impulse at omega equal to 0 and nothing else exists, okay. So this is my x of j omega, right. So there is a frequency shifting property. Now what I'm going to do is, so by frequency shifting property, so there is a formal proof given in the textbook as well, so you can take any path you want, okay. Ultimately the results are going to be the same. So I'm going to multiply x of t with a complex exponential, okay. And now the relation between the two Fourier transforms, I think it's 2 pi delta omega, okay. So when I multiply by an exponential in the time domain, what happens in the frequency domain is my x of j omega will be shifted by the appropriate amount, okay. So this is what will happen. So multiplying by an exponential in the time domain is equivalent to shifting your spectrum, okay, fine, right. So I'm going to make use of this property, okay. So which means, so if I multiply, what is x of t now? X of t is 1. So this implies that e power j omega c t has a Fourier transform x of j omega minus omega c, okay. So this can be easily verified. For example, so suppose if x of j omega is 2 pi delta omega minus omega c, let's say I'll take y, okay, so don't get confused, okay. So if I find the inverse Fourier transform, so my signal y of t is related by this formula, right. So this is my y of j omega, okay. So the variable of integration is omega. But as you know, the impulse function only exists when the term inside the bracket goes to 0, right? Which means this, the value of this integrand will not be equal to 0 only when omega minus omega c is equal to 0. For all the other values, omega not equal to omega c, right? So that by definition of impulse function, I know that it is equal to 0 for omega not equal to omega c, okay, right. So the integrand becomes fairly simple. So 2 pi gets cancelled with 2 pi, it's a constant. So my y of t is nothing but, so for all the other values, the product will be equal to e power j omega t into 0. So for when omega equal to omega c, this will become a constant, so I can take it outside, okay. So integral from minus infinity to infinity delta omega minus omega c d omega, right? So this is equal, this integral is equal to 1. So this is nothing but e power j omega c into t, right? So I have shown you the Fourier transform relation between these two. Okay. Now, what does modulation theorem tell you? So the modulation theorem states, if I convolve, or if I take a product of two signals, right? So my assumption will always be the same. So x of t has a Fourier transform x of j omega, right? So I will not take signal y of t and its Fourier transform I represent it by x of j omega, right? So if a signal is x of t, the Fourier transform, I'll denote the Fourier transform by x of j omega, and similarly y of t has a Fourier transform, right? These two are not periodic signals, okay, or they can be periodic, doesn't matter, right? Since we have defined this, okay. Now the modulation theorem states that, so if I have a product, okay, x of t into y of t, right? So I'll call this as a signal z of t, okay. So my Fourier transform z of j omega will be, right, x of j omega convolved with y of j omega, okay. Now this is what is used in all of your communications, okay, in one or the other way, right? So for example, so I don't know whether you learned or not. So there is something called as a Dsbsc modulation, okay, the double sideband suppressed carrier modulation. It's the simplest modulation that you can think of, right? So it's called Dsbsc AM, okay. So Dsbsc stands for double sideband suppressed carrier suppressed carrier, and AM stands for amplitude modulation, right? Suppose I have a message signal m of t, right? The information that you are willing to transmit, okay, or broadcast. For example, it might be a music or speech, right? So whatever the information that you are planning to transmit, so I'm going to represent it as m of t, okay, and there will be something called as a carrier signal, a high frequency signal, okay, which will be in the range of hundreds of kilohertz, okay, so which I'm going to call c of t, it's nothing but a sinusoidal wave. So I'm going to take a cos signal, okay. Now, so suppose, and this is your DSB modulation, right? So why amplitude modulation? Now the amplitude of the carrier, instead of being AC, right, it's message, okay, right? So the message is embedded in the carrier, the amplitude of the carrier, hence the term amplitude modulation, okay. Your message is modulating the amplitude of the carrier signal, okay. So how is the spectrum related? So my spectrum, suppose m of t has a spectrum or Fourier transform m of j omega, okay. So this AC cos 2 pi omega cos omega ct, I can represent it as AC AC e power j omega ct plus AC e power minus j omega ct by 2, okay. So this is by Euler's formula, right? So now I know what Fourier transform of e power plus j omega ct is, and what Fourier transform of e power minus j omega ct is. So and I also know the modulation theorem. So my y of j omega, right, has to be m of j omega. So I am taking a product in the time domain. So in the frequency domain, the spectrum is getting convoluted, okay. So it has to be this, right? So the spectrum depends on the message, whereas the spectrum of a carrier, right, is fixed, okay, because I'm using a cos as a carrier. So if I take the Fourier transform of this here, I'm going to get AC divided by 2 into 2 pi delta omega whenever it's plus here, you'll get a minus here, okay, plus AC by 2 into 2 pi, so delta omega plus omega c, okay. So when you are convolving with two impulse functions, so what you are going to get is, so 2 gets cancelled, so pi AC is common, okay. So m of j omega minus omega c plus m of j omega plus omega c, okay, right. So the diagrams are given in almost all the standard textbooks, so you can check what how is it related. Basically, if you whatever you have at 0 will now be present at minus omega c as well as plus omega c, right. So it's basically shifting of origin when you convolve with an impulse function. So this is your modulation, right. And it may be digital communication or analog communication, right. In one or other sense we'll be doing this, right. Hence all these terms will have a common term called as modulation, okay. So we'll be shifting the spectrum, right, from origin to somewhere else, okay. So this is what happens in a modulation, right. So that is why I told you, so these three properties together cover your communication, the whole of communication textbook, right. So if we assume that there was no noise, okay, fine, thank you, we'll stop here.